Hello and welcome to the second video from section 3.1. Okay, so then we're going to make a quick little definition before we get to our first theorem of this section. So the ij cofactor of an n by n matrix A is just a slight variation on what we've seen already. It's a matrix you get where, it's this positive or negative sign and the determinant of aij, where now instead of a1j, which we saw before, we're looking at the n by 1 minus n minus 1 by n minus 1 submatrix obtained from A by deleting the ith row in jth column. So previously we'd seen that the determinant was, a11 times the determinant of a capital A11, plus or minus, plus or minus, plus or minus. The plus or minus are all carried in here. And so these C's are just these determinants of these submatrices. So this is called the cofactor expansion of A across this first row because the weights are the values of the matrix on the first row. And the first theorem we get is that actually there's nothing special about the first row or the second row or the first column or second column. We could have computed the determinant using any one of these rows and columns. In particular, the determinant of an n by n matrix, can be computed across any row or column. So let's look at our old example. So last time we saw that, we very painfully, took 1 times the determinant of that matrix plus 2 times the determinant of, this matrix, minus 2, plus 3 times the determinant of that matrix minus 4 times the determinant of this matrix. And it was more work than it needed to be, for the simple reason that if we expand along this column instead of the first row, we've got 2 zeros from the very beginning. So we only need to do 4 times the determinant of that matrix. So minus 4 plus 0 minus 0 plus 6 times the determinant of that matrix. So let's see why. Let's do exactly that. Okay. Right, our theorem says the determinant of A should be equal to, what do we have here? A14, C14. We're going to work down this column. So this is A14, and then this is C14, or plus or minus the determinant of that. So then plus A24, C24, plus A34, C34, plus A44, C44. And the nice thing is that, A24 is exactly this term, A34 is this term, those are both 0. So since, what are we saying? This is 0, and that's 0, so actually the determinant is just A14, which was what? Just 4, actually. It was just 4 times C14 plus 6 times C44. So we only actually need to compute 2 determinants, 2 3x3 determinants instead of 4 of them, which we did last time. So let's compute those. C14. Remember, this is -1 to the I plus j, so -1 to the 1 plus 4 times the determinant of 0, 1, -1, 1, 1, 0, 2, 0, 5. Right, that's the matrix we get if we kill off the first row and fourth column. 205, yeah. Okay, and this we probably computed elsewhere, or I'll let you finish the computation. We're gonna get the same answer as before. I just wanted to show you how much easier it is if you intelligently select a row or column. So C44, -1 to the 4 plus 4 times the determinant of 1, 2, 3, 0, 1, -1, 1, 1, 0. Right, because that's what you get if you eliminated the last row and last column. You get this 3x3 matrix. And then check that the determinant of A is still whatever we said it was last time, right? Negative 12, negative 12. Okay. And there's like a little shortcut if you don't want to remember negative 1 to the I plus j. And the shortcut is the first one is positive, the second one is negative, positive, negative, and it goes back and forth like this everywhere. It alternates everywhere. So this is telling you what sign this thing was going to appear with in the expansion. So that's how I knew when I started a 4 here that we needed to start a negative sign. If you don't like that rule, the negative 1 to the I plus j always works. Okay, let's do another example. Maybe we want to compute the determinant of 4, 1, 3, negative 5, 0, 3, 1, 6, 0, 0, negative 1, 7, 0, 0, 0, negative 2. Okay, and if we were just staying at the definition, we would have to definitely have to compute 4 3x3 determinants, right? We would do 4 times that matrix, 1 times determinant of this matrix, 3 times determinant of, and so on and so forth, right? But we're clever people that we are. We're going to choose a row or column that makes this easy. So let's expand down. Go do the cofactor expansion down column 1. Because that's going to give us 0 times a bunch of things, and we know it's 0 is equal to. So the determinant of our call this matrix A. So our determinant, maybe let's call it, just say, never mind, we don't need to call it A. Just say that our determinant is equal to 4 times C11 plus 0 times C21 plus 0 times C31 plus 0 times C41. And we don't, yeah, the nice thing is that, okay, that just means that all we care about is C11. So what's C11 equal to? This is just 4 times, right, negative 1 to the 1 plus 1 times the determinant of the matrix we get if we ignore the first row and column. Okay, so then we just have 3, 1, 6, 0, negative 1, 7, 0, 0, negative 2. And we'll do the smart thing here again, which is, well, let's expand down the first column. And maybe you can see where this is headed. Where we're headed here. This is 4. That's just, yeah, this negative 1 to the 1 plus 1 hangs around. And it's times 3. Times, I guess you could do negative 1 to the 1 plus 1 again. And then the determinant of, or yeah, sorry. So there's this, which hasn't changed. And then this whole big determinant is what? It should be 3C, the new C11, plus 0 times the new C21 plus 0 times the new C31. But these don't contribute at all. So this is 3 times negative 1 to the 1 plus 1. Sorry, 4 times 3 times negative 1 to the 1 plus 1. And then the determinant of this 2 by 2 guy. Negative 1, 7, 0, negative 2. Okay, 4. I mean, these are both 1s, so let's just ignore them for a sec. 4 times 3 times, what are we going to get here? Negative 1 times negative 2, minus 7 times 0. That's too many parentheses. Okay, did it. So we'll notice this is actually just equal to 4 times 3 times negative 1 times negative 2, since that 7 minus 0 doesn't contribute. Okay. That's 4 factorial, which is what, 24? And the important thing to notice is that actually we can make a quick generalization here. So matrices of this form, where you've got zeros below the main diagonal, are called upper triangular. And I say this over here? Yeah, a matrix of this form is called upper triangular. It's a square matrix with zeros below its main diagonal. You can flip it over, like if we had only things below the main diagonal being non-zero and everything above the main diagonal is zero, that would be lower triangular. And in general, if A is a triangular matrix, upper or lower, then its determinant is the product of the entries on its main diagonal. And the proof is basically just this, that if you expand down this first column each time, you'll just pick up that number each time. So we've got a little shortcut for for computing determinants of triangular matrices. Okay, and that's all I have for sections 3.1. I'll see you all next time with 3.2. Take care, everybody.